person of a really remarkable, varied talents, I have to say. And I should tell you that he went to the University of Iowa as an undergraduate and then got his PhD at the University of Wisconsin, and then went as a postdoc to Caltech and has just soared up the ladder till now he's a named professor. Well, actually, he's been a named professor for almost 20 years, but we'll get an idea of why that's so. But anyhow, the way we know each other is because there's a testimonial to his adventuresomeness, is that some years back I had an idea, some of you may know, that dark matter might have hadronic interactions and be able to stick to nuclei, and in fact might have a mass that was sort of like a deuteron mass, and so it might be hard to tell an isotope that was really an exotic binding of a nucleus and one of these dark matter particles compared to just an isotope with 2 more nucleons. And so I started, but the predicted abundance level could be as small as 1 part in 10 to the 10th. And so being able to measure the mass well enough, you wouldn't confuse it with just a down state, an extra 2 nucleons, and at that incredible level is highly non-trivial. Nobody had ever even tried it in that mass range. Anyhow, so I started searching the web to see who does, stuff that's really hard, and found his lab. And then I think I emailed you, I didn't just call you, and asked, this is during COVID, and said, would you potentially be interested in this? And it was fantastic. He just jumped into it and he said, gee, it's COVID, I'll just do it myself instead of assigning it to a guy. So hopefully we'll get that written. It didn't find it, unfortunately.
My next visit, I'll talk about that.
Okay, yes.
But only
yes.
if you give me the model predictions so we can write our paper.
Anyway, well, I'm not too happy with the answer, so. But I gotta live up to it, and.
Well, there's some sort of principle here. If you look for dark matter, they call it dark for a reason, but you're not gonna find it.
It's getting more and more elusive. Anyhow, it's very great pleasure to have him finally visiting in person. Thank you.
Hey, well, thanks so much.
Oh, and I have to advertise his talk tomorrow, which will be equally and more interesting, at 3:30, with time for discussion after.
So in this room?
In this room.
Yeah, thanks very much for the invitation. My wife Jane and I are really having a great time. We rolled in last night and are having an apartment in Lower Manhattan, and the department here is really remarkably congenial. It's a great space to hang out in. I really had a good time talking to students an hour or so ago. So Glennis and I know each other through this dark matter project. Why are we talking about dinosaurs? This is a highly improbable topic for a seminar given on this floor, I would imagine. There's a couple of reasons for that. One of them is dinosaurs. Who doesn't like dinosaurs? They're monsters that ruled the earth. You have to be interested in them. They're just intrinsically interesting. The deeper reason I wanted to present this work here is it shows you an example of how the principles of chemical physics and our understanding of quantum mechanics of the chemical bond, combined with a sufficiently good measurement, allows you to solve problems that seem sort of unsolvable superficially. So what we're going to be doing is measuring quantitatively, as if you stuck a rectal thermometer right into a brontosaurus and counted to 10 or whatever you're supposed to count to, and measured within, like a degree, the body temperatures of these animals that have been dead for 100 million years. How is that remotely possible? And we'll see. Okay, so that's what we're going to talk about. And the connection to physics is, if you are having trouble remembering the physics of 1900 to 1930, this will be great for you, because that's the limit of my understanding. Everything after that is your job. Everything before that, I accept as my job. Okay, so there's a deep background to this problem. Let me see if I'm getting, yeah, everything's there. Yeah, so people have known about fossilized remains of dinosaurs for literally millennia. So we have descriptions of what must have been dinosaur bones going back well over 1,000 years. And they just didn't have any idea what they were. They thought they were like bones of gigantic people, who knows what, okay? The first really organized description of the dinosaurs came from Sir Richard Owen, a British naturalist, who classified them based upon physical characteristics reconstructed from sort of almost accurately reassembled skeletons. And he says the combination of character, such as the sacral bones, so the hip joints, altogether peculiar among reptiles, others, as it were, borrowed from groups now distinct from each other, all manifested by creatures far surpassing in size the largest of existing reptiles, that's the giant monster part, is sufficient grounds for establishing a unique group, the saurian reptiles. So here he's saying they're big, they're kind of like reptiles in terms of their skeletal characteristics, but their hips are strange. So what does that mean? There are two different groups of animals, the therapsids and large reptiles that were loosely contemporaneous with the earliest dinosaurs, that were similar in size, and if you sort of blur your eyes and look from a distance, they will remind you of each other, except these ones were walking around in a ridiculous way, okay, with their thighs having to stick out at an angle from their body due to the construction of their hips. And these ones were walking around in a way that would seem familiar to you if you went to South Africa and looked at megafauna roaming the landscape today. Basically, they can get their body weight up onto their back legs without having to splay them out. And this made them much more mechanically well-suited to moving around the landscape. So some peculiar things about them, they're really big. Like, this is why we remember them. It's why we like going and looking at their skeletons in the museum. There weren't very many little ones. So the average size of a mammal is like the size of a big rat. If you just like add up all the mammals everywhere, make a frequency distribution of their sizes, a normal way to be a mammal is to be like a kilogram. And so somehow, the dinosaurs, there were very few of them smaller than 10 kilograms. You might imagine, oh, they weren't well preserved. We have old fossilized mammals, and they were small. So for some reason, there was some sort of advantage pressure to being really big. Okay, and they lived all over the place. They were on every continent, lots of ecological range.
Can I ask a question?
Yep, shoot.
Were there also reptiles with hips like modern reptiles that were smaller? Or was it just
Yeah, for sure. So, and you know this. So you know there are alligators. You know there are crocodiles. You know that there are iguanas. There is a full spectrum of size range in reptiles with poorly designed hips. Somehow it works for them in their ecological niche, and over a vast range in size.
but not up to this size?
Oh no, this would be.
So is it?
I don't think there are marine reptiles with their body weight supported by buoyancy force that could get to 50 tons and above.
I guess I'm just asking if that hip, whatever it's called, architecture is better for much larger.
Yeah, it's
reptiles.
definitely better for being really big.
Yeah.
Absolutely. So, but as you'll see over the course of the talk, there might be other reasons for being really big. Like you get to stay warm. Much better if you're big. Okay.
It seems that the same difference in this hip design is observed in the difference between chicken and duck.
I'm not so sure about that. Okay, tell you what, this evening I will eat a chicken, you eat a duck. And tomorrow morning, we're gonna have a sit down. We're going over it, yeah.
But okay, so if you go up to the Museum of Natural History, which is my level of authority here,
Yeah.
and you go to the Hall of Dinosaurs, what they will tell you is that dinosaurs and birds are the same, right? That there's not a meaningful distinction between dinosaurs and birds.
I mean, this
Right.
is sort of nonsense.
Well,
yeah.
but that's, and so it's, I mean, at some point, there must be a bunch of dinosaurs that are under 10
We're gonna get
kilograms,
into
right?
this. So the phylogenetic, line of descent from root reptiles through many branchings. Some dinosaurs remind you more of birds, some of them less, some are closely related, some are less closely related. They will eventually emerge into all sorts of modern organisms, including birds. And so if you had to draw a line from birds back to anything, yes, you will end up in the more bird-like dinosaurs. And that'll be one of the things that we'll explore with the measurements that I'll show you. But to say that the dinosaurs were basically birds, this is like,
Well, I guess what I'm saying is, if birds came from dinosaurs, right?
Yeah.
Like at some point there had to be a bunch of things that were less than 10 kilograms.
not necessarily, not necessarily. What if they were big and then they got little?
They got the feathers and the fly and everything.
They
and then
absolutely,
shrunk.
they got feathers. There were tons
Right.
of dinosaurs that had lots of feathers,
Right.
no flying.
Right.
Yeah, they had feathers for other reasons, presumably staying warm. Feathers are good if you want to stay warm.
Yes. Big bird.
Yeah, plus birds have beaks. Lawyered.
So did
Yeah.
flying dinosaurs. They had beaks.
Pardon me?
Pteranodon had a beak. Quetzalcoatlus had a. I have a 5-year-old, so you have no idea how many dinosaurs I know.
Okay, counter lawyer.
Does the bad hip design mean that it's less likely to be big, and is the bad hip design also seen in dinosaurs, or is that more like a moderate
No,
level?
this is a defining characteristic of the dinosaurs is they had good hips for supporting weight.
Actually, so you mentioned this. You said that they were in every continent, and this is stressed all over. Like this is typical of North America. But 200 million years ago, every continent was connected, right?
No, well, I mean,
200 million.
that's like, go on. Where are you going with this?
No, I'm asking what is the significance
The significance is
their
they were
distribution if
capable,
everything
they were
was.
capable of occupying a vast range of ecological niches. Okay, so they were able to live places that were hot, cold, wet, dry, and so forth.
So I have a comment about the bad versus good design,
Yeah.
because the bad design is the one that the alligator and crocodiles have, according to this. And these
they're
guys
not
have been
dead.
around for quite some time, and
Which would you choose to have? Okay, you go in and you get your hip
I'm not-
replaced. You have to have your hip come out like this or like this.
I mean, I'm just saying, no, but
Afterwards, you
it's
can
not,
tell.
it's not
Yeah.
really- they've been around for, they're a very successful design. The fact they've been around for so
They're
long,
good at something, okay?
they're good at the
something.
thing that makes them be around for
Okay,
many millions.
Let's keep rolling. Keep rolling. All right, we're gonna get through slide 4. 4 of 80 or whatever it is I did. Okay, so people have been trying to interpret, how do I put some meat on the skeleton? Okay, how do I look at the skeleton, reconstruct it, imagine what this thing looked like alive, picture it moving across the landscape. This active imagination is the beginning of reconstructing physiology, ecology, metabolism, all of these different interconnected things that you might want to know about them. And here is ground zero, is the hiring of an artist in preparation for the Crystal Palace exhibition near London. Benjamin Waterhouse, he made these gigantic statues, some of which you can still find in, I forget which part in London. There's one of them still there. So these things, they were hollow, and associated with the crystal, the exhibit, they opened one up and held a dinner inside of it. So the takeaway thing from it though is like not necessarily that they're hollow and they had funny meals inside them. Look how ridiculous they are, okay? They look like big potatoes. They look awkward, heavy. They don't look like a living thing, okay? It's challenging to come up with an understanding of what these things are like. And I have to say, I'm part of the problem. So this is, my mother dug this out when I started working on dinosaurs and reminded me that when I was 7, I wrote a 6-page paper about dinosaurs. It was called Dinosaurs Roar, and I also had a lot of misunderstandings about them. So dinosaurs were the dumbest animals that ever stepped foot on the earth. So you can tell, this is basically, I'm gonna trash them. Like, that's where this talk is going. Sometimes they sat there when they were being killed. Why did I think I knew that? Somehow I thought I knew that. So this whole project is an attempt to like work my way back to some sort of reasonable understanding. So most people, I think, who have like a passing familiarity with dinosaurs, they understand there is this question about whether we should imagine them as being, resembling the large reptiles that we encounter at the zoo or something, or out in the landscape like alligators. Cold-blooded, we'll get more in a moment about what that means exactly. Relatively lethargic, okay? They can sprint, they might move around energetically for 30 seconds or something, but they are not continuously active. Awkward, dumb, so forth, or are they this sort of reconstruction where we pull their legs up under themselves, thin them out, make them look a little bit more athletic, make them vigorous, make them clever, aggressive, okay? So which of these end members should we be thinking of when we reconstruct them? There are more scientific, more specific, more precise ways of trying to conceptualize this, to break down this problem into potentially measurable things. And the one that we'll focus on, because it has a consequence that is, it has a physical variable that you could potentially reconstruct, is body temperature. Were they homeothermic like us, that is, they maintained a continuous body temperature within a narrow range, okay? Or were they poikilothermic? They varied, individuals may have varied in temperature with time and environment, they may have differed from one another, evolved over time, what their normal body temperature was. That's just, you don't have to have any specific interpretation about why. It's a measurable thing. They either all had the same body temperature or they had variable body temperatures, okay? And then once you have some understanding of what their body temperatures are, now you're ready to talk about why. And the basic question about what's regulating their body temperature is it mostly set through metabolic heat production, or is it mostly set by exchange of heat with the environment? Do they have a thermostat and they metabolically regulate to some temperature, whatever it is, high or low? Or are they completely at the service of whatever the environment is doing to them, to make them hot or cold or whatever? This then connects to physiology, the metabolic heat production. And the two end members that we recognize are tachymetabolism, where you basically upregulate your basal metabolism so that you are always ready to go. Your body temperature is elevated and your enzymes are active, you're ready to roll. Or bradymetabolism, you down-regulate your metabolism when not necessary, upregulate it when necessary. This tends to be complicating. You're switching enzymatic pathways for your energy-generating metabolisms between your down-regulated and upregulated state. You have to maintain a variety of them. There's some sort of lag. You probably can't stay in an elevated metabolic state for very long. And so there are compromises that have to be made.
What was the Earth's temperature when dinosaurs were around?
Not radically different from today. Yeah, a little more. Yeah, maybe on average 3, 4, 5 degrees warmer, tops. Okay, you have a question, somebody? Okay, yeah, shoot.
Is there a particular association between these levels? Like, will we
Yeah,
ever
so,
have like
so
endothermic?
like for example, we have a tachymetabolism that allows us to be endothermic. Our body temperature is internally regulated. Okay, when you walk into a cold room, you don't get cold. Well, you might feel cold, but your core temperature doesn't change. And we are homeothermic for that reason. We have a thermostat that has a set point. We stay there. Thank you. Okay. Heterothermy is I change my mind from day to day or year to year or evolutionary generation to evolutionary generation. I vary in my strategies. Okay.
Modern reptiles, where do they fall on this?
Modern reptiles, you would say like a small lizard would be this end member. Okay. The that they absolutely have a Brady metabolism. They will cool off if you put them in the refrigerator or whatever. And their body temperature oscillates. Okay? And then there's finally an idea that will become important once we start looking at data, gigantothermy. What if I wanted to maintain a big body temperature, but I didn't want to spend the metabolic energy to run my thermostat hot? One solution is just be a ball of meat the size of this room. My heat generation, even at a low basal metabolism, is proportional to my volume. My heat exchange is proportional to my surface area. So long as I don't collapse like a blob or something, I win, okay? I don't have to spend the energy and I get to stay warm. So gigantothermy is a strategy that people have speculated about. We see in some modern animals like big bluefin tuna. Their body temperature is elevated above seawater temperature. And they do it by recirculating blood through their active muscles, conserving some of their heat, and just by being big. Okay? So why would you want to be warm-blooded? To have a tacky metabolism and be endothermic. And the main reason is that your enzymes have an ideal temperature of operation. And this varies, what is the ideal temperature for an enzyme? Well, if I look across all of life and all the different archaea and bacteria and so forth, yes, there's a diversity. But for the key enzymes in metazoans and animals and things, it's pretty narrow range. Like we like to be active at an elevated temperature, something pretty close to our body temperatures. And if you get much hotter than that, you start denaturing your proteins, and now you're dead. And if you get colder, the chemistry is just slow. Okay, and so there's an ideal, and you'd like to stay in that ideal, even though it is elevated with respect to surface temperature, and surface temperatures vary. So how do you do that? You do it by metabolically regulating yourself to that temperature. But there's a cost, and it's huge. Okay, so this is energy demand, so that has to be met by eating sandwiches and hamburgers and whatever it is that you eat for various clades of organisms. And to first order, like an average small lizard and a songbird are basically the same size. And they're not really ecologically occupying that different of niches. They both like to eat bugs, they're both little, so forth. This one is eating 20 times what this one is eating, or more. So in one day, this one has to eat what this one eats in a month. That is an enormous tax to have to pay. And you will frequently fail to pay it and end up starving.
I mean, another huge energetic cost is flying.
Yeah, these are related things. So if you're gonna fly, you obviously have to have like wings and be prepared to pay the cost of flying. You also have to have stores of metabolic energy in your muscles ready to burn. You have to maintain that. And if you're just sitting, if you put wings on a crocodile, it can't fly.
Right.
Yeah.
But like, so if you take a bat,
Yeah.
does a bat look more like a songbird or like a mammal?
A bat, I don't know for sure, but I would guess that a bat is somewhere in this range. Yeah. Okay, so how frequently if this is a competition, I have to survive, and if I keep myself upregulated and warm, and I adapt to that metabolic style, I have a big advantage in the moment, but a big cost on the back end. So how commonly does evolution choose warm-bloodedness? Not much, okay? Mammals and birds, they seem familiar to us. It seems like, oh, of course, this is the natural end result of evolution, that you will make this choice. Not really. Most animals choose being cold-blooded. And just to give you a sense of how unusual the balance, the trade-offs lead to this selection, there are warm-blooded sort of plants, okay? Why? Because it gives them a very specific advantage in a very specific situation. So skunk cabbage stores carbohydrate in its roots, and then in the late fall releases it back up to its flowering whatevers and warms them up so that they're visible to insects and draw pollinators. And they do it at a time when all the other plants are sleeping because it's too cold. Okay? So it's an adaptation to specific situations. Yeah.
So obviously this isn't what plants are doing, but the mammals that, or not the mammals, the animals that don't, that like aren't endotherms, do they have the same enzymes and they're just operating at lower efficiency? Or
Well,
do they have different
I don't know. Okay, first of all, like I'm not an enzymologist,
Yeah,
so
I mean, just like in your heart, whatever.
yeah, I know that the cold-blooded animals that are familiar to us, they have to have multiple sets of metabolic enzymes that operate at different temperatures.
When you say endotherms are very rare, you're using number of species as a measure, right? You're making a list of all species and saying endotherms are a small fraction. But if you use biomass, for instance, wouldn't you get a completely different answer?
I'm not so sure about that. So biomass, I mean, the dominant biomass in the oceans is like shrimp and stuff. I mean, they're not really, the biomass that
7 billion humans weigh quite a bit.
we're a small fraction of the biomass. We're not that.
I think there's way more ants than there are people by mass.
Be a fun calculation, we could.
Yeah, off to the order of magnitude physics lab. Right. Error bar is king. So, also, we're not as endothermic as we sometimes think. So if you undergo anesthesia, your body's ability to control your basal metabolism falls apart. And if you stayed under anesthesia for like a day, your body temperature drops and drops and drops and drops, and eventually it gets to 35 centigrade, and now you're getting hypothermia. So you will die unless somebody intervenes and keeps your body warm, because this regulation, it's a kind of high-level thing. It's the icing on the cake. It's not fundamentally how your body has to work. You choose to operate your body at elevated temperature. We're also familiar with hibernation, so a bear's basal metabolism drops radically when they hibernate, and their body temperature drops by 7 degrees centigrade, which is a lot. Sloths, okay, they evolved from other mammal groups that we assume, without data, but we generally assume that they had basal body temperatures, core body temperatures like our own. These ones are quite a bit colder, okay, like a hibernating bear, but all the time. And then finally, hummingbirds, when they undergo torpor, so they basically get very, very, very sleepy when the weather's cold, their body temperature will drop by tens of degrees centigrade, and the minimum that's been measured, close to the freezing point. So this is a recoverable thing for them. They can just turn off their tacky metabolism, and for a few hours, have a brainy metabolism, and have a body temperature that looks like a lizard. Just to preserve energy. Okay, how are we gonna figure out where the dinosaurs fit into this system? Okay, so a very old argument, and the one that you hear at the museum is, dinosaurs remind me of birds. Birds are warm-blooded. Well, birds are one of many things that emerged through the forest of different sorts of clades of organisms that evolved out of the root reptiles, okay? Other things that emerged were the ectotherms. So why do you think that that dinosaurs were like birds? Why don't you think they were like alligators? They also came out of those same groups. How am I supposed to relate, and who's to say that this is a unidirectional thing, that you always go in one direction? The sloths show us that you can emerge from mammals who are presumably warm-blooded and yet be relatively cold-blooded. Okay, feathers, another argument. So you look at a bird-like dinosaur that seems obvious that it flew and had feathers. Well, why wouldn't it have a metabolism like a bird? It seems like it would help it enormously. I can also find a 9-meter-long, non-winged dinosaur with feathers. It was not flying, okay? The feathers were for something else. So the relationship between metabolism, feathers, flight, this is muddled. Okay, we don't really know what is the order in which each of these things came together to permit birds to fly around like birds. Okay, another argument that gets raised is to get a sense of the energy budget of an animal's metabolism by looking at the ratio of predators to prey in their ecosystem. One of the more horrifying facts I've ever heard is that an ecosystem containing spiders can be like tens of % spiders by weight, okay? They can basically live off of bugs similar in mass to themselves, and that's a sustainable ecology for them because they don't really need very much food, okay? At the other extreme, all of our familiar megafauna, modern mammals, lions and whatever, they have to be a small fraction of all the biomass in their ecosystem so that they can harvest enough food to keep their engine burning. So when we try to reconstruct something like a tyrannosaur in this sense, you would say, oh, they were warm-blooded because they were a capstone predator that was feeding off a huge mass of other animals. They must have had high energy demand. Maybe they couldn't eat the things that were around them. Okay, who's to say who was prey and who wasn't? So if they run across a 100-ton titanosaur, maybe that's not dinner to them. Right? Also, taphonomy or preservation may have compromised the record. And who's to say that the scaling laws apply 1, 2, 3 orders of magnitude higher in size? Okay, another argument comes from bone histology, looking at the textures, the sizes of bones, their vasculation. One side of this argument says dinosaur bones were fibrous and well vasculated, like ours. Therefore, they were like mammals. On the other hand, their bones are generally banded, okay, meaning their growth was seasonal. That's more like reptiles, or like this. So it's an ambiguous argument. A recent addition to this is a sort of qualitative, semi-quantitative, new sort of biomarker study, looks at the Raman spectroscopy of organic molecules preserved in bone, and notes that there are bands corresponding to chemical moieties that are part of the protein structure that holds the bones together, and notes a correlation between the presence of some of these chemical moieties and basal metabolism in extant animals. They then create a transfer function to predict basal metabolism and correlate it with body size, and then they note there's a bimodality. Okay, this is like not my argument, this is their argument. And their argument is, I have cold-blooded animals that include fossil reptiles and some dinosaurs, warm-blooded organisms that include fossil mammals and other dinosaurs, and that I can create a sort of genealogical tree using such data that shows warm-bloodedness appearing and disappearing at multiple points in the family tree. Generally speaking, folks have looked at this and said, I don't know, you lost me at the correlation part. that they don't buy that there's a direct line part. Okay, another argument has to do with growth rate. Okay, if you can reconstruct how much, taking advantage of the annual banding in bones, you can figure out how long it took a dinosaur to grow to full size. And they did it fast in comparison to modern crocodiles or really big prehistoric crocodiles, suggesting maybe they had a high metabolism to support that high growth rate. I don't know. I'm a simpleton in this area, but I assert that I'm not a reptile. Yet I am the size of a small crocodile, but it took me a long time to grow that way. So like, what does all this mean? I don't understand how you're going to get there. Okay, so something that would be, not definitive in every axis of these issues we're talking about, but it would really be nice if you just had like a quantitative number that measured heat content, okay? Like temperature. Could we know their temperature? That would be very useful. And we could then compare it to environmental temperatures, if we had a way of reconstructing that, and to body size. And there are three sort of end-member cases that we might expect to see. Elevated body temperatures, warmer in general than environmental temperatures, invariant with size, like modern mammals. Okay? Whales, mice, they're basically the same within the range we're discussing here. Then we would turn and look at reptiles, and we would see they do follow strategies to elevate above environmental temperatures. They bask, they grow seasonally, and so forth. It doesn't get them very far. They're still substantially cooler, a good 5 to 10 degrees centigrade cooler in all environments. And that would be true across the size scale. Or maybe dinosaurs followed gigantically. They made themselves get warm just by being big. And that's part of their bigness. That's part of the point of being big, is that you get to stay warm. Okay.
So is there that gigothermy line, that's not?
That's from a physiological model. So that's like, if you really keep digging, what's behind this model? Some like sketchy data. But it is a quantitative prediction of how this is supposed to scale based upon extant animals and a few scaling laws.
A big dinosaur has to be small when it's a baby, right? So
You're right. Yes, exactly. Okay, here's what I wanted to do with all of this, but I'm afraid I'm not gonna be able to show you. I wanted to make a map of a big dinosaur's body temperature, every part of it, from the little finger bone to each tooth. You'd imagine the head is probably warm, body cavity warm, extremities colder. Why not? If I have a fossil remains of the whole thing, I should see it all. So unfortunately, preservation of fossils doesn't let me do that. But you're right. So ontogenetic, over the lifespan variation is absolutely a thing you might predict. Okay, so this is supposed to be impossible. This is like a famous dinosaur guy. He says, "You will never measure the body temperature of a dinosaur." I say, he says you. That's because you didn't figure out how. Okay, so the way we're going to try to do this is using a sort of chemical physics of isotopes effect. And like I'll give you a couple little physics slides, but I hesitate to do it because like you're actually physicists. And all of this is like the physics of 1932 or something like that. But it's mine, like this is what I have, so I'm gonna hold on to it. Okay, so the starting point, of course, is the naturally occurring isotopes. And we tend to divide them in my field into those that either undergo radioactive decay, or they're products of radioactive decay. And these obviously vary in their abundance mostly over time. And so we don't really focus on them. They experience the same chemistry effects that I'll focus on, but they're hard to interpret because the radioactive decay part overwrites that or interferes with it. So we're not going to be paying attention to those. Instead, we will focus on the naturally occurring stable isotopes, things like deuterium, that are part of the nucleosynthetic stew that our solar system inherited from the cosmos, but their chemistry is subtly different from the chemistry of their isotopically lighter relatives. And that's what we're going to be paying attention to. By the way, the word isotope is just a neologism, means same place in the periodic table. It's usually credited to Frederick Soddy, who did the measurements of the molar mass of lead, which he found to be variable from sample to sample, and a variety of other measurements like that. The word actually came from Margaret Todd, who was an early pioneer of women in medicine in Britain in the early 1900s. They apparently were friends. They met at a dinner party. She's like, "Hey, what's going on, Frederick? What's new?" He says, "I just discovered there's like different kinds of lead atoms. What am I going to call them?" She says, "Isotopes." That's it. She dropped the mic and walked away, and he used it. Okay, so why are we interested in them? A quick primer reminder. We describe the motions, interatomic motions in molecules and in unit cells and minerals and so forth as a family of harmonic oscillators. Yeah. And each of those oscillators we can approximate as like having the properties of a mechanical spring. So the harmonic oscillator equation describes the frequency, and the two master variables are the spring constant, how stiff is the chemical bond, and the reduced mass of the motion. And then we bring in the quantum description of energy contents of systems that undergo vibrations. and building on Debye-Einstein theory, say, I'm going to say all of these modes of motion exhibit quantized energy content, yeah? And then bring in the uncertainty principle, and I recognize that my energy is not only quantized, but it must include a minimum energy level, the 0-point energy level, okay? Each of these energy levels follows Planck's postulate that energy is proportional to frequency. That's really all we really have to know about that. So then in the 1930s, a cast of characters pulled together the threads of the early 1930s quantum mechanics and tried to figure out quantitatively, with experimental validation, how it described the behaviors of chemical bonds. If I have a quantum mechanical energetics of chemical bonds, what are then the implications for how bond strength varies with things like isotopic content? And Harold Urey got his Nobel Prize for discovering deuterium, not just because he discovered an isotope. Lots of people had discovered lots of isotopes before Urey discovered deuterium. It's how he did it. He did it by enriching. How did he enrich deuterium from natural hydrogen? He did it by the vapor pressure isotope effect. He boiled off H2 and kept deuterium in the residue. How did he know to do that? Because he had a quantum mechanical model of what the intermolecular bonds were like in the liquid. And he knew that a heavy isotope substitution changed them. And so it is the connection of this emerging theory of the quantum mechanics of bonds with an experiment. That's why you get the Nobel Prize for that. Gupta Mayer, she was a super important person in early nuclear theory. And then she also had a student, Jake Beagleisen, who didn't get a Nobel Prize, but is lovely anyway, so he gets a smiley face. And they together, basically, Urey first comes up with a description of the chemical physics of energetics of chemical bonds in isotopically substituted substances, but it's awkward. And then Mayer and Beagleisen come in and tidy it up and make the version that we used. Okay, the basic concepts that they're working with are that when I do a heavy isotope substitution, I raise the reduced mass of the oscillator. The Born-Oppenheimer approximation tells me the electronic structure doesn't care. And so the spring constant of my bond stays unchanged. Therefore, there's a frequency shift that is inversely proportional to the square root of the reduced mass change. Okay, it sounds like, oh my God, I learned about this when I was like a freshman. Okay, did you really though? Because we're going to use this. It's going to be very important in about 3 minutes that it works that way and not in some slightly different way. Okay, and then if I raise the reduced mass and drop the frequency, I lower the energy. Every chemical bond in the world energetically wants to be heavy isotope substitute. Okay, if I could have all the atoms in the entire Earth be heavy isotopes, the Earth's free energy would drop. So it's a desirable state. Yeah?
I think this is going to your point later, but it's not the free energy that would drop.
The enthalpy, yes. Yeah, exactly. Yeah. We're almost there. You're right. You said it better than I did, but I'll say it like you said it in just a minute. Okay, and so putting this in the context of our description of the quantized vibrational energy levels in a chemical bond, deuteration of something like HCl drops the vibrational energy of each of these levels. Okay? So now, how do I get to a thermometer with this? Well, first of all, let's see how this plays out in systems that have 2 or more chemical species. This is how Urey thought about it. Urey looked at this effect and said, I'm going to create tools for the study of the Earth and space and so forth using this chemistry. And his first thought, and his best thought, was I'll think about what it means for a system of carbonate, a common ion in waters and a major constituent of many geological solids, and water, common solvent. I bring in an O18 atom, and I slow the vibrations. If I put it in the water, I slow the vibrations in the water, I lower its energy. Now I have a system that is lower in total energy than the one I started with that had no heavy isotopes. If instead I put it in the carbonate, because of the nature of these bonds, they're stiffer, there are more modes of motion that get slowed, it's actually in net energetically better in terms of the vibrational energy content, the enthalpy term, if I put the O18 there, okay? And so the carbonate ion wants to steal the O18 from the system, and it's a dilute constituent. So the molecules are all fighting each other for these things, assuming they're undergoing reversible chemistry. Okay, and so putting it again in terms of these energy wells, the water has a subtle energy drop on substitution, the carbonate has a deep energy drop on substitution, and so I'm driving the O18 into one of these things. Fighting this is the configurational entropy term. I want to have a more random system energetically, and the hotter it gets, the more I want that, okay? The free energy of the system is the enthalpy term, which is basically scaling with the vibrational frequencies, minus the temperature times the entropy term, which in these systems is mostly configurational, okay? So at high temperature, I want to have a random state where heavy isotopes are shared, and at low temperature, I want to have an ordered state. How ordered? Well, at interstellar medium temperatures, these effects could be factor 20, factor 50, factor 100. At Earth surface temperatures, they're like 1%, something like that. Okay? So I have a temperature dependence where the separation of O18 between coexisting compounds is strong at low temperature, weak at high temperature. And there's an enormous literature of using the exchange reactions associated with this trading of isotopes between molecules as thermometers. This is how the climate history of the Earth was reconstructed for the most part. The problem is the temperature is proportional to the equilibrium constant of this reaction. That's a function of the isotopic content of something I find in the geological record, like a mineral, divided by the isotopic content of the water it grew from. I have lots of fossil carbonates, I have no fossil oceans. I don't know what the O18 content of the water was. I can make assumptions about it, they're usually not as good as people would like, but in the case of the body water of a dinosaur wandering around on land, drinking from lakes, breathing out moisture from its breath, excreting all these things, you have no idea, okay? So you're really guessing what the O18 content of the water is at a level that makes the temperature estimate.
What about ice?
What about ice?
Yeah. Like from the poles. If
Yes.
you dig really deep,
Yeah.
you might find ice layers.
The oldest ice on the Earth that we know of is about 7 million years old.
So dinosaurs are all killed by that.
That is true. Everything melts.
So can't do it. So we're dead in the water, right? There's another version of this, okay? And that is to look not at the trading of rare isotopes between coexisting molecules, but the state of ordering within a single molecule, single population of molecules. So let's consider a simple dimer like molecular hydrogen, and let's say the reduced mass term, which is the only one we really care about, the first order, is in this case a half, okay? So it's 1 times 1 over 1 plus 1, 1/2. If I have a single deuteration, in round numbers, now it's 1 times 2 over 1 plus 2, 2/3. I've dropped the frequency in proportion, and I have a frequency shift, which is the energy, okay? If the frequency drop is proportional to the energy term, the enthalpy term I care about, okay? 589. What about 2 deuterations?
Sorry.
Yep, 2 deuterations, 2 times 2 over 2 plus 2. This is the energy shift. And in case your arithmetic is impaired this afternoon, this is more than twice that. That means if I take trace defects of deuterium and I drop them into a population of H2 molecules, and I allow them to come to an equilibrium state, a lowest free energy state, it is better to have them stick to each other and have a single doubly deuterated one. That's better than 2 singly deuterated ones, okay? There's a driving force to organize the isotopes into groups, into clumps, we call them. Why do we call them clumps? Because when this got invented, somebody said, oh, you need an acronym, like with 6 letters where each letter means some silly thing. I was like, no, I'm gonna make everybody say clumps. That sounds funner to me. It will sound much sillier that way. Okay, and in terms of our energy well, we have our unsubstituted small energy drop on single substitution, more than twice that energy drop on double substitution. And this effect is also temperature dependent. In fact, Urey was focused on this. This is how I came up with all of this for geochemistry, is reading Urey's papers from the 30s. He actually wasn't interested in HD. He was interested in D2 and calculating, predicting, and experimentally verifying this ordering reaction. That is what he thought would be a definitive demonstration of the quantum mechanical nature of the bond and its response to reduced mass. So great, let's take that and then make it a tool for studying natural materials. Okay, the system we're looking at are the carbonate ions. Carbonate ions are in your blood. They are undergoing acid-base chemistry that keeps them sort of titrated to a narrow range of concentration. And they are very reactive and exchangeable. So they're trading oxygen atoms with water in their environment all the time, very fast. And therefore, they are gardened to an equilibrium state. We can use principles of density functional theory, molecular dynamics sorts of models to predict how the ordering of the rare isotopes into the same carbonate ion should scale with temperature. And it is a thermometer. It's very subtle, okay? So between oceans boiling and oceans freezing, that's about 0.3%. 0.3% of a thing that is very rare. I have one rare isotope, I have two rare isotopes, that's rare squared, 0.3% of that, almost nothing. And that's the full amplitude. I actually want to measure like a degree. I have to somehow do this at levels of like 10 to the minus 5 in order to get it right. Whatever, you measure perfectly, doesn't matter how small the effect is. So that's the only test. It's sort of like the Steve Martin thing. Where you say like, okay, how do you become a millionaire? First, get $1 million. All you have to do is, it's easy, just measure it perfectly. It's like no big deal. So our targets are carbonate ion groups that are trace substituents in the phosphatic part of tooth enamel, and then in eggshells, which are mostly carbonate. So they're a better target. The way we do it is to dissolve them in phosphoric acid, which is an anhydrous acid. It means that the oxygen in the carbonate doesn't exchange with the oxygen in the phosphate groups. And then we do a gas source mass spectrometry measurement. And like there's a lot of different sorts of isotope mass spectrometry. Tomorrow I'll talk about like some exotic, elaborate sounding types. This is like really basic, just engineered for precision and sensitivity. So the way that we do it, to overcome the fact that we need a really precise measurement of a very trace species, is we draw on a design that Al Neer put together in the mid-40s. This is like right after he discovered uranium-237 and was doing mass spectrometry sort of associated with the run-up to the Manhattan Project. He then invented a really precise, the first precise isotope ratio mass spectrometer. And the important components of this are a capacity to have a sample in standard in identical conditions in parallel bellows, and they go back and forth, bleeding into capillaries. And the capillaries are designed to have purely laminar flow conditions, so no turbulence in the gas, no diffusive fractionations, none at all can be tolerated. I have a really bright, stable electron impact ion source. The mass spectrometer itself is sort of crude, it's just a single focusing magnetic sector. Simultaneous detection of all the ion beams, so any fluctuation in performance gets averaged out, or canceled out rather. And then for this measurement, we have to read the rare beams through very sensitive resistors, and they have to be very stable. So the engineering of those resistors, which was done by Thermo Fisher, was an important part of this. And then you just have to be like really, really, really patient. So every single acquisition is like hours and hours and hours, and a single data point is a couple of days. Under standards, it's like a very time-consuming measure. So here we are doing these measurements on modern eggshells. We're seeing more clumpy means cold, less clumpy, more random means hot. There's a temperature scale, don't worry about the units, this is like whatever. And you can see the resolution of warm and cold-blooded organisms. We do the same things for teeth of some warm and cold-blooded animals. compared to their known growth temperatures. And now we're ready to go out, and this has been, those are data from quite a while ago. This has been redone a few times since, but it basically looks the same. And now we encounter the preservation problem. We go out and start looking at fossil remains of animals that we supposedly know about, okay? A woolly mammoth is just like an elephant, okay? So of course it'll be like an elephant's body temperature, we would imagine. If we look at the enamel of their teeth, that's exactly what we see. They see just consistent with any other warm-blooded animal. The dentin of their teeth, which is a soft organic sort of composite, that's been altered. Okay, the diagenesis, the chemical transformation during burial in just a few thousand years has destroyed it.
N here.
Pardon me?
You have some variable N here in previous slide and you didn't say what it is.
Those are samples from the same macro specimen. So multiple specimens, multiple teeth from the same organism.
It's a little strange because you have values 4, 3, 2, 2 and then average is 6.
Because that's the average of the enamel. And there's 4 plus 2 every day, that's 6.
4 plus 2 is 6, yes,
Okay,
but
yeah.
not average.
It's just the total number that he's
Of the
averaging,
enamel,
that
yeah.
he's,
The total of the enamel is 6.
this uncertainty
is over
must be
6, yeah.
reflecting that, that's
Yeah.
where it enters, right?
Right.
It's
Yeah,
just
the
it's
standard,
the
that's right, that's where the standard error code is. Okay?
Why are the error bars so different on the temperature?
Because
Because the dentin's all messed up.
The bottom dentin is plus or minus 0.2.
that's statistics of small numbers.
Oh, these are not error bars, these are just.
Those are
This is
replicate,
just
yeah,
the
those are
rate of
replicate
measurement.
statistics. Yeah, those are replication statistics. Generally speaking, this measurement is shot noise limited, but then if I do a small number of observations, it'll obviously do. Okay, so the important point of that is sample selection. You have to find and demonstrate that you have well-preserved things. So now we go back in time and look at alligator, giant shark, mammoth, rhino, pig, and we're seeing the warm-blooded, cold-blooded distinction that we expect. Okay, now we're ready to start looking at dinosaurs. So the first dinosaur we look at is a big sauropod, or 2 of them, okay? Here's 10 of these, 5 of those. And error bars are of order the size of the symbols. And they sure look warm-blooded, okay? So basically, if you walked up to one of these big sauropods and put your hand on it, it would feel like a cow. They are absolutely normal, large mammal body temperature. Now we start looking at eggshells, which are a much more accessible sort of sample, where you see a range in body size. It's because you're not sure how big the animal that laid the eggshell was. You're guessing based upon correlations with broader populations of specimens. But now we're starting to see the largest sauropods have body temperatures that can exceed those that we see in modern mammals, but don't exceed the line of death, okay? Even though the gigantothermy model would have predicted that they might have. More importantly for our purposes, as we start to see smaller sauropods, we're seeing lower body temperature results.
So I think there's something I'm missing here, which I'm sure is true, but like the isotopes can't exchange once the egg is laid or once the tooth is
Only if they
shed.
undergo, so there's 2 mechanisms by which the isotopes can exchange in the solid. One is solid state diffusion, which the mechanisms are kind of funny because they're sterically constrained by which oxygen can trade with which neighboring oxygen. But that process basically kicks in around 150 degrees centigrade. So until you get into like the petroleum generation window of temperature, this isn't an effective process. The second way it can happen, this can happen at any temperature really, is dissolution reprecipitation, reaction with groundwaters. The first of those things you really can't see happening. It doesn't leave a record in the solid. You have to avoid it by picking specimens that didn't undergo deep burial. The second process you can test for by doing things like cathodoluminescent mapping of trace metals, electron backscatter diffraction mapping of crystal orientations, things like this. So you can texturally characterize the samples, and obviously you're doing your best. They're complicated materials. but this has been done. We're picking things that look fresh to us.
So you're measuring the temperature when the tooth was forming or when the eggshell was forming?
That's the idea. The carbonate groups are so exchangeable in an animal's body that they're continuously equilibrated, as far as we can tell. And then once they die, that solid no longer turns over, unless the geological environment dissolves it.
Wait, so after the tooth forms, but while the dinosaur is still alive? This is
Oh, those are, yeah, that's an interesting question. So the residence time of organic matter in your bones is of order a decade. And so I'm sure that an adult dinosaur is resetting its own composition of its bones over time, slowly, but it's happening. We know this from like carbon-14 dating of body parts of animals, that only a few tissues actually retain their isotopic content over time.
Do you have any idea how old dinosaurs got to be before they?
Oh, that's a good question, before they snuffed it. They reached adult size around 10. It's sort of a rough number for the ones that are big enough, you would say, yeah, that's a dinosaur. So 10 tons or something like that. They reached that size by about age 10. I don't
10
know.
years, 10 tons
10
or
years.
10 years, that's pretty good growth rate.
Not that I doubt the megalodon was cold-blooded, but I shouldn't be worried about like these teeth sitting at the bottom of the ocean undergoing.
No, you shouldn't worry about that. There is, if they are exchanging as they sit down there, our expectation is that we'll see it in other properties. So it is things that we measure other than the temperature that can be used to sort. And there's a lot of metrics. People use crystallinity and trace elements, blah, blah, blah. So all of that is like part of the art of trying to do some natural samples. Okay, here's some more samples, these sort of derpy looking ones. Several of them, they are reinforcing this idea that I can have low body temperatures when size drops below some critical threshold. Okay, and then the things that look sort of like birds, their eggshells are variable in temperature and include low temperatures. So two other groups have subsequently dug deeper into these bird-like dinosaurs, and both of them found exactly the same thing. That subsets of the samples are low in body temperature, sort of like reptiles, and another subset is elevated. And this is now 3 different studies, different groups of samples, different ages, different organisms. This variability seems to be a repeated finding. So the warm body temperatures for small bird-like animals, some of the authors have concluded this is evidence of endothermy. What about the cold ones? Okay, there's just as many or more that are low in body temperature. So this is a peculiarity. It seems inconsistent with the idea that they universally used endothermy. Okay, and then another important detail, the eggshells are really only rarely are they definitively associated with a specific organism. You usually can say like, oh, this is like one of the ones that was kind of like a bird. I'm not sure which one. So who's to say that they all had exactly the same metabolic strategies? Sort of like sloth, in 100 million years from now, if a cockroach scientist found a human skeleton and a sloth skeleton, they might say, this is a 10 to the 2 kilo mammal. I'll bet their temperatures would be the same. Nope, they're different by 10 degrees. So. Okay, and then here's a couple odds and ends, a marine reptile and another weird dinosaur. So here's an overview, and our basic finding is that everything over a ton more or less conforms to the gigantothermy expectation. That you have a variance, that variance is loosely correlated with size, and it spans the range from cold-blooded to warm-blooded things. The small bird-like ones, we just see tremendous variance uncorrelated with size. And what does this mean? Is it ontogeny? They have like a youth where they're cold, maybe when they're egg laying, they can get warmer. Is it evolution? Is it environment? Unclear. They are clearly not uniform homeotherms.
Night and day activity.
Maybe. It's all we have eggshells, they're variable in temperature, that's what we know.
If you're an alligator.
Yep.
And you're laying
I'm
eggs.
not.
Marines.
Getting out in front of this, or you know how these things
No, wait, but you know, if you lay eggs in the summer and you lay eggs in the winter, would you then like?
First of all, you wouldn't.
Okay, you don't, and also your egg probably doesn't have the shell or whatever, but you know what I'm saying, like cold-blooded animals that lay eggs,
Yeah.
would you see that?
So I don't wanna like over-interpret why. The point is, they do not have, as a group, a uniform metabolic strategy that regulates them like modern birds do. All of the things you mentioned would not lead to variance in this measurement in modern birds. And so there's something about their temperature regulation that is not keeping up with all of these factors. Whatever the factors are, they are not covered. Okay, a last bit, I'm sure we've gone over, but let's look at one last thing. Somebody very recently looked at giant sharks up to 100 tons, really, really big ones. And the basic finding, it's easier to visualize in this figure that you've been looking at, is that the biggest ones are on average warmer than ones the size of great white sharks today. This is a little hard to interpret because the ocean varies wildly in temperature. And so you could make an argument, oh, they like to live in shallow tropical water, and they like to live 100 meters deeper in the thermocline. So these sorts of arguments could be made, but it's also consistent with the biggest of them elevating their temperatures above environmental temperatures, the way tuna do to a lesser extent, and the way the dinosaurs. Okay, so we're basically done. The takeaway, I would say, is that sauropods are broadly similar in body temperature to ourselves when they were big. So you could say they're warm-blooded in a very simple sense, but the evidence suggests for different reasons. That basically, they only got that way when they were very large. And that overall, gigantothermy is probably a better description of how their body temperature was regulated. And the same may have been true of the biggest marine animals. What's next? So if you have to have like a takeaway understanding of what the dinosaurs were like, I like this person's statement that they were like damn good reptiles. They were reptiles, they were cold-blooded more or less, but highly adapted to success in their environment. Better skeleton arrangement, nice and big so they don't cool off in cold climates, more competitive at being the megafauna that dominate the landscape, but not mammals and not warm-blooded like we are. Where next? I'd say the best things to explore are these questions about the variance in the small bird-like animals. So first of all, it addresses where did birds come from? How did they become the way that they are? But it also, that's the part of it that I don't think we have any physical model that says why they vary like they do. The gigantothermy one, there's a model, and the data look like the model. So so far so good. The birds are just variable for unknown reasons. So exploring why. Is it their age? Is it their living condition? Is it their, who knows what? Are they different evolutionary groups? So, okay, I'll stop there. We've probably gone over it.
Well, that was really.
Well, thank you for all your questions. I have to say, like, going to a seminar where people will talk to you is great.
We
Yeah,
have
yeah.
a reception following, but let's take a few questions so everybody can share, but do come down for the reception. if you like.
I was thinking about this spread in the smaller onesie, so I was wondering whether there's any correlations in brain size relative to body size and temperature.
Yeah, you would love to know this, but the fossil evidence is, at best, an egg with an embryo inside of it. And in those conditions, you can basically assign them at the level of family or something like that. You're really not getting species level identifications. And most of the samples, you don't know that. Most of the samples, you just have a shell. And you're saying, this reminds me of the shells from the dinosaurs that are this size. There's more sophisticated arguments about the nature of their nests and communities and whatever. These are all stories. You don't really know. exactly how to associate the animal with the shell. I think the most definitive thing to do is we get specimens, the specimens are rarer and the measurement is more damaging to the specimens, but we have to do the teeth enamel from these bird-like dinosaurs. So we can say this specific animal had this specific body temperature.
Yes, maybe what Mark was getting at, but if you take sea turtle eggs or something in the modern world, so sea turtles lay eggs on beaches all over the place, and some of those beaches are warmer and some are colder, maybe some years they're warmer, and you just look at the temperature of those eggshells, would you see a similar sort of variation?
So this is even more interesting than that. So there's a student from Cambridge visited my lab last summer to do a project where she wanted to understand how environmental temperature influenced the sex of sea turtles, because the sex of the at birth is set by the temperature of incubation. And so she wanted to know, as you warm the environments where these animals live, are you going to bias the balance of sex of the animals in the population and therefore impact their ability to reproduce? So the problem was their shells are basically leathery, many of them. And they're subsets of turtles and other small reptiles, geckos and things she also looked at. Subsets of them have a carbonate mineralized shell that we can study in this way. Others of them, it's a leathery shell that's basically an organic glue that is not suitable for this measurement. So I don't know, we did not succeed with this study.
Sherma had a question.
I have a more general question. It's of course incredibly impressive that you can measure temperature of this beast. What else can you measure?
This is it. Can't do anything else. No, I'm shot. Totally shot. No. So this measurement was the founding measurement of an entire sort of approach or school of studying isotopic structures and things. And it began with the capacity to measure doubly substituted small gaseous molecules like CO2. And we can get CO2 out of the carbonate minerals, and therefore you see the measurements that you saw. So that was invented like 20 years ago. That was like a foundation stone for trying to do all of the isotopic forms of everything. Like there's 50 million molecules known to science. Most of them are organic molecules that have of order 20, 30, 40 atoms. Those species exist in a near infinite diversity of isotopic forms, different numbers of substitutions, different locations of substitutions. And so the capacity to study all of them required a radically different technology from sector mass spectrometry. And I'll show you a little bit about that tomorrow. But basically, we can measure lots of other stuff. So the main application space is understanding the reaction networks, either biological or non-biological, that create organic compounds in natural environments. If I come to a natural environment after the fact, I don't know exactly what happened, and I recover organic molecules, can I figure out specifically and quantitatively how each of them was formed and how they relate to each other? And that's sort of the design purpose of that technology, but other people are using it for other things, like metabolomics of disease and environmental chemistry and so on and so forth.
Are you assuming that the abundance of O18 in the atmosphere of these animals was the same as it is currently?
Okay, so this is an important point.
Could you repeat the question?
Are you assuming that?
He can repeat it.
Yeah, that the abundance of O18 in the atmosphere around these animals was the same as today. So the point of measuring this clumping effect, the state of organization of the rare isotopes, are they stuck to each other or are they separate into separate molecules? The point was to overcome this uncertainty. We don't care whether the same O18 content prevailed in the environments for these animals because we're not measuring, we're not focusing on, we have to measure it anyway, but we're not focusing on the concentrations of either carbon or oxygen isotopes, which depend on diet, rainfall, how much they breathed that day, I don't know, like a million things. We'll never figure that stuff out, sample by sample. So we focus instead on the state of organization. the isotopes in this particular case. You'll see another case tomorrow, briefly, where we do exactly the same thing, but on aromatic carbon from meteorites and from the Ryugu asteroid. And we're asking there, is the chemistry happening in the interstellar medium at tens of Kelvin, or is it happening around the envelopes of carbon-rich stars at 1,000 Kelvin? And there, the signals, now instead of having to measure, 10 to the minus 5 relative changes, we have much, much bigger amplitude signals that we're looking for, but it's the same concept. We're not using the abundance of the isotopes to tell, we're using their structure, organization.
Well, this is, one more,
All right.
okay, and then.
I will
down to
echo
the
that it's very cool.
line and stuff.
Is the reason you can't do bones because all the carbonate has been replaced?
Yeah, unfortunately, fossil bones, even like a bone you throw out in your backyard, if you do that, I don't know if anybody does that, come back a year or two later and it's dead. Like you will find a thing shaped like a bone, but already the remineralization has begun. And the basic problem is that the crystalline phosphatic material, the apatite in it, yeah, there's crystals there, but they're really, really, really small. And they're basically a composite held together by an organic matrix. And the crystals are just much more reactive. They have high surface area to volume, they're in a reacting medium, they dissolve and reprecipitate, and they're shot very, very quickly. Which is too bad, because I really, really wanted to make a fully detailed map of a T-Rex's body temperature, where you could visualize it.
So if they have a beak, there's nothing you can do.
Yeah, beaks I think are honestly, I don't know, but maybe they're like keratin or something.
You can only do the eggs, right? So.
I mean, we can make, as I was mentioning, we can make measurements of this type and more on organic molecules like proteins in hair or something like that. But that chemistry is irreversible, and it doesn't really record the free energy minimum of the system. It's recording other things, inheritance from substrates, rate constants of reactions, progress. So that is recording the reaction network and its details, not the environmental condition.
Well, what could be a better advertisement